Okay, welcome everybody. My name is Bill Davids. I'm a professor of civil and environmental engineering at the University of Maine. And I'm here today to lead a webinar titled FRP Composite Girder Technology, Evolution and Continuous Improvement of Design, Manufacturing, and Construction. This is the second in a series of two webinars. The first one was held on 6/06/2022. I'd like to recap that with a couple of slides before we get started, just to orient everybody. And the first speaker in our webinar on June 6th was Wayne Frankhauser, an engineer with the Maine DOT. And he gave us a lot of background on their experience with FRP composites. He covered a lot of topics in general: buried composite arch bridges, E-glass FRP bridge deck reinforcement, pile wraps, HC beams. We moved on after that to focus on the FRP bridge girder, the GBeam, that's been developed here at UMaine and is being commercialized by AIT. And I spoke about the initial development, really focusing on motivation for that, mechanics and behavior, design and fabrication and initial testing, as well as some work on the shear connector, initial work. And that really took us from 2015 through about 2019, early 2020, at which point Anthony Deba of AIT Bridges took over and talked about the design of the first such structure to be put in service, which is the Grist Mill Bridge in Hamden, Maine. There was a heavy focus there on girder fabrication and placement, some of the advantages that were realized during construction. And think of this slide as something to get us all oriented with what this particular girder system is, and it's really a visual recap of the second and third presentations from our last seminar. The rendering on the left shows that GBeam girder bridge, or a general GBeam girder bridge. You see it's a hollow tub section. It's not filled with concrete, although there may be a continuous concrete diaphragm at the ends. It's got a concrete deck, and there are shear connectors. That concrete deck and the girder act compositely. And the GBeam itself is a hybrid system. It's got a carbon fiber bottom flange. It's got plus minus 45-degree E-glass webs with a foam core to help prevent buckling, solid E-glass flanges. And in terms of applications, this is really a direct substitute for a steel or concrete girder. And it can be used for simple spans of up to about 100 feet. It could be pushed further than that. It really becomes a question of what it's economical to fabricate or what we can fabricate at any given time. There's no limitation to what we can produce in terms of the physics or how it carries load. The picture on the lower right is a photograph of the Hamden Grist Mill Bridge, the first such bridge of this type completed. It's 2 traffic lanes plus a sidewalk on US Route 1A in Hamden, Maine, a few miles south of Bangor. 75-foot span. It's got 5 girders spaced at 8 feet on center. Very typical of what you'd see with concrete girders or steel girders, and it's an 8-inch concrete deck. Total span to depth ratio on that bridge is about 15.5. So this is a well-optimized design for both bending strength, shear strength, and deflection control. Now, today's talk is going to really cover what's been happening in the last 2 years. I'm going to be speaking to the continued development of the GBeam bridge girder, which has it's been ongoing for a while. And it's some really significant work has taken place and advancements have taken place in the last couple of years that are now being deployed out there in the field. That's where Anthony Deba will take over, talking about manufacturing and installation of the GBeams, more as they're done today and how they'll be done in the future. And again, a lot of work has been done, a lot of progress been made on how these girders are made and options for installation. And then we'll close with a Q&A and a panel discussion. And please, I encourage you to type your questions into the Q&A chat box, and I'll be moderating after that, and I'll be going through those questions one at a time, and Anthony and I will do our best to answer them. So to get started, let's talk about continued development of this GBeam bridge girder. There are 5 major topics that I want to hit today in about the next 20 minutes or so. First, the field load tests of the Hamden Grist Mill Bridge that we did in late 2020 to assess the in-service performance of that structure. As the first of its type, it was really important to go out and load that bridge and assess how it behaved. We also want to talk about what we're doing now in terms of Girder-Deck shear connectors. So there have been major advances made there. We've also taken a look experimentally at creep response of the girder. That's a bit of an unknown going into this. It's not something where we can just say, well, camber the girder for 1 times the dead load deflection, which is pretty typical for a concrete girder, which also undergoes creep. Because again, this is a hybrid with FRP and concrete behaving compositely together. We've also spent a lot of time taking a closer look at girder web shear capacity. And then I'll briefly touch on ongoing and future research, because the work, of course, to this point is not done. So field load testing of the grist mill bridge. We did a field load test back on New Year's Eve in 2020. It's not the best time of year to test a bridge in Maine, but we got lucky. As you can see from the picture on the lower right, we didn't have much snow on the ground and it really wasn't that cold. So overall, it could have been a lot worse. I won't tell you it was a lot of fun, but it could have been a lot worse. And our objective is to figure out how does this bridge behave under large service live loads? Does it agree with expectations? Now, we've done a lot of live load testing at the University of Maine of a number of bridges, 3 dozen or so over the last 10 years. So we have a lot of experience with it. We went out there and installed 23 reusable strain sensors at critical locations. We had 3 sensors over the depth of every girder at midspan. We also put some sensors at the girder ends, and that's important, as we'll see later. We put a lot of weight on there. We put 4 overloaded dump trucks on there, about 65 kips each. We had, I think, in total, 262,000 pounds on the bridge, and they were put at predefined locations. And you can see from that aerial view on the lower right, for example, we're backing those trucks up together to get those heavy tandem axles as close as possible to midspan. We're moving them transversely across the bridge to load different girders more heavily. So a lot of thought goes into how we load the structure and where we place those trucks. And what we're trying to do is maximize loads on individual girders to as great an extent as possible. And then we go take these flexural strains and we compare them with expected values. So here are some typical results. These are the largest strains that we measured in the central girder, and that's the most heavily loaded girder. Girder 3 is the third of 5, the one right in the middle, under a 4-truck load. And one thing jumps out at us right away. If we have 3 girders over the depth of the section, three gauges, one near the bottom, one at the middle with a red line, and one near the top of the beam. And we see that all of these strains are tensile. We're peaking at about 320 or so microstrains, significant strains in the middle, also significant tensile strains at the top of the girder. The strains vary linearly over the section, as we'd expect. But this also tells us that the neutral axis is really up in the concrete deck. And that's important because that means, yeah, we've got full composite action out there in this bridge, as we would expect to see. Now, that peak strain of 318 microstrains, though, are standard design calculations with usual AASHTO live load factors, ignore non-structural elements. They predicted about 935, almost 3 times as much strain as we observed in the field. The question, of course, is why? We almost always see less strain in a field test than our design calculations predict. That's usually because of conservatism in live load distribution, non-structural elements like wearing surfaces, curbs, sidewalks, railings contributing to girder stiffness or bridge stiffness, but we don't see a factor of 3. So there's something else going on here. And it's a good thing, we learned this lesson a long time ago, it's a good thing that we put some gauges near the ends of the girder. So this is that same girder 3 in the same test, and these are strains measured at the bottom and mid-height of that girder at both ends of that girder. And we can see that we're getting significant negative flexural strains. That implies that we've got some negative moments at the end of the girder. It's a simple span. Why would we get negative moments? Well, the picture on the right, the drawing on the right, shows why we likely saw those. We have a heavy integral concrete diaphragm that runs the full width of the superstructure, rebar threaded through holes in every girder. And we can see that that also supports, via a little shelf, the concrete approach slab, which is doweled to that diaphragm. So that is going to tend to partially restrain the ends of the girder against rotation. That certainly could induce some negative bending. Not something we'd account for in design, not something we can really quantify, but it's definitely there. So we took a closer look at this. We built some really high fidelity finite element models using solid elements to discretize all the concrete components, explicitly modeled the girders with shell elements. We modeled steel railings, integral curbs, the sidewalk, all these non-structural sources of stiffness. We also put at those concrete diaphragms at each end of the bridge some linear springs that would allow that to capture that rotational restraint. So as the bridge deforms, the ends rotate, those springs are activated. And then we went through and we determined through a minimization procedure what that spring stiffness was. We minimized the difference between the measured strains and the model predicted strain. So this is a calibration process, a tuning process. We don't know what the stiffness of those springs should be. But indeed, if we go through that exercise, you can see from the first and third rows in this table that we can pretty closely match what we measured in the field. And that gives us more confidence that that rotational restraint from that end diaphragm is a likely cause of the negative strain at the girder ends, i.e. that partial rotational restraint of the girder ends. And I should point out that the nominal finite element model with no springs on the end predicts higher strains, of course, than one with the springs on the end. And those strains, however, are smaller than those we get from our design calculations because that FE model, of course, includes curbs, railings, sidewalks, all these other elements which tend to stiffen the structure. That FE model will also more accurately predict our live load distribution to the girders. So we took a really deep dive into this data. We looked at it very closely, but the important message here, the real takeaway, which is in the blue box, is that those field live load tests really verified conservatism in our design calculations. So as we would hope and as we would expect, the first instance where this girder was put into service is a conservatively designed structure. We have not only redundancy in it, but we also have other load carrying mechanisms and that are helping us out. They're nothing we would count on in design, but they're there, they're real, and that's always good to know. Now, another critical issue here are those Girder-Deck shear connectors. And if you recall from the last webinar, the original connectors used in the first pilot girder test, the 40-foot specimen, had poor fatigue resistance, so we had to redesign them and come up with new connectors to use in the Hamden grist mill bridge. And those are shown in the figure on the right. They used A490 bolts. They were in direct bearing with the girder flange, and they transferred shear directly. They required a bolt spacing of 6 inches on center. It's pretty tight. It doesn't sound that tight compared to shear studs in a steel girder, but you know, that's 2 connectors at 6 inches on center, and that's a lot of bolts, and it's a lot of really tight tolerance holes that have to be drilled in each flange because you have to get good bearing between that bolt shank and that girder flange with no slip. The net result is they're fairly expensive to fabricate. They also, since they're not galvanized, are prone to corrosion, and they can corrode. I wouldn't say they're prone to it because they're on the bottom of the deck, but they're not highly corrosion resistant. So that necessitated really the development of something that would give us a positive shear connection, at least as good as this, but would be simpler to fabricate, rely on fewer fasteners, maybe allow us to use corrosion-free fasteners. So what we explored starting back in 2018, 2019, and it took several years of development, was coming up with a connection system where we have a textured flange surface. The upper surface of the top flange of the girders, as shown in the picture here on the left, it actually has sinusoidal ridges that are formed in there during the infusion process. So as that girder is infused, we have a caul plate that sits on top, and it's not bonded to the girder, but that caul plate has matching ridges, and we infuse resin up in there, and we create these sinusoidal ridges. And then when we cast it against the concrete, as you can see from our shear block specimen in the middle, we get matching ridges on the concrete deck. So now we're transferring shear by mechanical interlock between the concrete deck and the top girder flange. Picture on the right was just taken a few weeks ago. That's a girder that we fabricated in our lab for one of our research sponsors, the U.S. Army Erdick Center down in Vicksburg, Mississippi. And you can see how that translates, how those are formed in a real girder. You can see the fasteners sticking up out of there. And those fasteners are now spaced at 12 inches on center, not 6 inches on center, 50% fewer connectors. And we can also use now, we proved that we can use a stainless steel threaded rod for that connection. So we don't have to worry about keeping threads out of the shear plane. We don't need to worry about using a high fatigue resistance material. We can go with stainless steel. It's 100% corrosion free. Much simpler to fabricate because not only do you have half as many holes, but those holes do not need to be tightly toleranced. They can be cut pretty roughly through there because you're not relying on that bolt bearing on those holes. Those bolts are doing nothing but keeping those two deformed surfaces together. We've completed an extensive round of fatigue testing and strength testing and clearly demonstrated that this connector possesses infinite fatigue life and plenty of capacity for the strength 1 loading case. And this is the connection system that in general is being used on every bridge moving forward from this point. Another aspect of the girder behavior that hadn't been previously explored but really needs to be accounted for is creep. When we put a concrete girder bridge out there, we understand that it is going to continue to deflect with time under its own self-weight. I've seen it. I'm sure some of you have seen it. Driving over a concrete bridge, you can see that permanent deflection that's in there. If it wasn't cambered properly to basically come down to straight or flat after some period of time, usually 6 months, a year, 2 years. It's a bit of an unknown with the FRP girder because it's got a concrete deck, and FRP itself is subject to some creep deformation, not maybe as much as concrete, but it's not creep free like steel is at normal operating temperatures where we don't really worry about creep. So to assess this, we had a specimen built 55 foot long. It actually had a full depth precast deck on it. This was a very substantial deck thickness as well. That's shown here in the lower left. And we monitored deflections of that single beam with dial gauges for about 200 days. And that deck was poured on a continuously supported girder 61 days prior to the start of the test. So it had the concrete on there that may have been shrinking and undergoing some deformation, but the girder itself couldn't really deflect because it was continuously supported. And then we basically had it brought into our lab and we took the supports out from under it and started reading deflections on that girder. And by coincidence, or not coincidence actually at all, that is the same girder that we tested to failure in a strength test after we're done with the creep test. And I showed the video of that test in the last presentation. So this is the same beam. It first underwent these creep deformations. And this is what we observed. So this is a plot of creep deflection versus elapsed time over that roughly 200-day period. And we see some initially higher creep deflections, and then it does tend to taper off a bit, about, in round numbers, about 0.4 of an inch, about the maximum creep deflection that we observed. We see some bouncing up and down because it was inside, but there are temperature changes and humidity changes within the lab. They do tend to affect deflections a little bit. And the calculated dead load deflection for this particular beam is 1.2 inches. So the creep deflection we measured was only about 0.4. So the total creep and dead load 1.6. So that is actually very encouraging because we're creep deflection we measured is about 1/3 of our initial dead load. However, our total measured deflection at the end of the test was not 1.6, it was actually 2.1. So what we think actually happened is there's also some shrinkage deflection that occurred. And during those first 61 days when that girder was fully supported, we can do a calculation. We can estimate what the shrinkage induced deflection would have been as the deck underwent AASHTO specified, standard concrete mix shrinkage. It would have been about 1/2 inch. And that deflection, when the girder was supported at the ends, would have been mobilized as that shrinkage strain was released. And we would have ended up at 2.1 inches, which is about the total we measured. So at the end of the day, this is actually very similar to a concrete girder bridge where it's pretty typical to specify at least a camber of at least 1 times the dead load deflection to account for creep. Sometimes it's a little bit more, but that's sort of a minimum value that I recall from my time in practice. Now, another really important aspect of design is girder web shear strength. I haven't talked about that yet, didn't talk about it in the last presentation, other than to say that these girder webs have ±45 E-glass on them. They're a foam core web, so we can use less FRP and we can still prevent buckling there. And the design, we believed to date, has been pretty conservative. We used a shear strength for those webs of about 10 KSI. That was based on some early coupon tests according to an ASTM standard that really isn't designed to assess the in-plane shear strength of foam core panels. I should point out that 10 is a knockdown, incorporates a knockdown factor of about 0.85 to account for statistical strength reliability. So the mean shear strength would be somewhat higher than that, but the design value is 10. To better assess shear strength, we made a pretty significant investment in an ASTM picture frame fixture. And this is a particular test, D8067, which is designed specifically to determine in-plane shear strength of foam core FRP panels. And you can see a picture frame test on the lower left. So this has got 4 edges of a panel that are attached to a fixture that's fully pinned. And so we have this diamond configuration, and we put it in tension. When we put it in tension, we're inducing a state of almost pure shear stress on that specimen. And you can see from the picture on the lower right, we monitored shear strains during the test using digital image correlation, and we got a very uniform strain field in there. Those are the shear strains DIC predicts, and you see from the colors that it's pretty uniform shear strains, especially as we get towards the middle of the specimen. And we ran 12 tests of 2 lamina specimens. So these had 2 E-glass FRP lamina on each face of that foam core web. And those tests gave us a reasonable lower bound mean shear strength of about 18 KSI. I say lower bound because we got edge failures on these specimens. We didn't actually get a material shear failure, but we got failure in bearing of the fasteners on the edge of the specimen before we actually reached its shear strength. If we applied our statistical strength reduction factor of 0.85, that would take us down to an ultimate shear strength for design of about 15 KSI. And that in turn would get knocked down by a fee factor, an environmental factor, what have you. So we apply a significant factor of safety beyond that. But this is very encouraging. It tells us that our designs to date probably have been on the order of 50% stronger than they need to be, 10 versus 15. And so we've designed them, they've been over-designed to some extent in terms of web shear strength. However, with a girder web, it's not just about the material strength, it's also about buckling. And this is a topic that has seen relatively little investigation. So the buckling strength of foam core panels subject to in-plane shear is not something you'll find a lot of papers on. There are a few out there, but it's difficult to do experimentally. It's not trivial to even explore this analytically. You have to be quite careful with analytical or numerical simulations. So to date, we've used, again, what we believe to be conservative estimates, and for our specimens and the bridges that we've designed, because it's challenging to accurately quantify, and we really had to dig in. And we have been digging in over the last year or so, and we've run a very significant suite of finite element simulations. Here on the left shows actually the results of one of those graphically. This is the buckled shape of a foam core web panel, simply supported on all edges, subject to pure shear with an aspect ratio of about 5:1. The reason we choose an aspect ratio of about 5:1 is as it gets larger, the buckling capacity doesn't really drop much after that. And it actually is a high aspect ratio because unlike a steel girder, which is also very much subject to web buckling, we can't put stiffeners in there. We can't develop tension field action. We can't build panels into this. It really is an unstiffened web. We've run many, many simulations like this to develop figures like the one you see on the lower right, which is the shear buckling stress resultant in kips per inch. So that would be how many kips per inch a face sheet can take before it actually buckles. And for different ratios of the foam core thickness to web thickness. So that foam core to web thickness ratio is shown there. And we run this for a variety of different face sheet thicknesses, and 0.12, 0.36, 0.6, 0.96. And this particular plot would be for one girder depth. And we'd run this for many, many girder depths, and we would come up with a result like you see here that would allow us to predict the buckling capacity of a foam core web for a typical girder. What we found does indeed verify that the designs to date have been pretty conservative, that we have not been erring. We've been erring on the side of caution, let's put it that way. But this work is ongoing, but it's very encouraging, and I think it's going to be very helpful for design in the future. Now, to summarize our recent research findings from this, so our field load testing has definitely demonstrated good in-service response. And we've got conservatism in there. We expect that. but our girder flexural strains are similar to expected values given the partial end restraint that we observed. We can verify that. And our FE models, of course, they do better with live load distribution. They can capture all the other sources of stiffness like integral curbs and wearing surfaces and sidewalks and things that we don't account for in design. And they explain what's going on in the field. We've made a lot of improvements to the Girder-Deck shear connector, and that shear friction connection is a lot more efficient. And again, you can move to 100% corrosion-free superstructure. And I think we've made some significant strides when it comes to creep response as well as web shear strength. And these are important questions. These are things that when it comes to practical design, you need to know how much do you have to camber that girder. You need to be able to confidently predict the shear strength of the web as well as its buckling resistance, because that is a limit state for the design. And our ongoing and future work is building on this and adding to it. So one thing we're actively doing right now is developing a design guide for these girders. So this is in progress, and it will allow a designer to quantify moment resistance, shear resistance, design the number of shear connectors that are required. And we're developing methods that allow this to be done either in a detailed fashion using moment curvature analysis for bending, for example, as is done right now. But it can also be done with a simplified method with a straight line approximation to a nonlinear concrete stress strain curve. May still be iterative, but is something that could be coded in a spreadsheet and equations are laid out for a designer. And that would allow some preliminary design or an estimate of the size of a girder that could be refined if needed in the future. We're field load testing 2 bridges this summer to gather more in-service data. We're going to retest the Hamden Grist Mill Bridge, and we're going to test a second bridge that's being built in Maine this summer. And these will be instrumented not just with flexural strain gauges, but with shear strain gauges, rosettes as well. And the objective here is to really get a handle on what's the live load distribution between girders. And let's see if we can develop some live load distribution factors or formulas that parallel what's in AASHTO right now, but are specific to the GBeam. Right now, we have to borrow distribution factors for other beam types, and we'd really like to know what's happening with this particular girder. We want to evaluate the shear connectors as well using other materials. We're in the midst of looking at using FRP threaded rods instead of stainless steel for that frictional shear connector, running a series of fatigue tests and control specimens. We'll also be testing 2 more full-scale girders, and that we expect to be commencing late this fall or this winter. We're hoping to fatigue test a girder as well, not just strength test it, to assess its in-service fatigue performance as a beam. And then a third one is developing a method of pultruding the girders, making the cross-section in a pultrusion process as opposed to vacuum infusion. This will make it basically higher throughput, and it should be more economical. This is a longer-term effort. Some of our initial work on the design of the cross-section to permit that is just getting underway at this point. And my final slide, I want to emphasize there is a good deal of public domain documentation out there. We have 2 journal articles just published in 2022. The first one is technically coming out in like July, but it is available and as a PDF file. We also have a conference paper that will, again, technically be published in July, but that obviously is written, that had to be done. And we have final reports on TIDC projects. Project 3.4 is up there. 3.1 and 3.14 will be available very soon. And I'm giving the website down here where these can be accessed. And I think after the seminar, we will follow up with a link to that so you can see them. And 3.4 is there now, and it has a lot of information and a lot of documentation about the field load testing and other things. And the others will talk about things like beam testing, connector testing, web shear buckling, all this stuff that I've touched on today will be detailed in that. And if you're interested in any of these and you have any trouble getting your hands on them, just shoot me an email and I will get you a PDF file with the appropriate citation. And with the exception of 3.1 and 3.14, as they're not quite done yet, okay? But they will be very soon. So at this point, I'm going to turn it over to Anthony Diba. I'm going to stop my screen share. And Anthony is going to follow on with a discussion of the current practice in terms of installation, fabrication of the GBeams. So Anthony's an engineer at AIT. His primary role there is the design of these FRP composite girders. His first project was the Grist Mill Bridge in Hamden, Maine, and he's got his fingerprints all over the other projects that are completed or ongoing that I'm sure he's going to talk about today. And he was also a grad student at UMaine. He was very involved with the initial development and testing of this GBeam bridge girder. So, Anthony, you should be all set to go, correct? I see your screen.
Yep.
All right.
I'm all set. Good afternoon, everyone. Thank you, Dr. Bill. So the first thing I'm going to talk about is when we got the grist mill project, we needed a mold to fabricate these girders. And it was just whatever we need and as fast as we can get it. And after talking with numerous people in the industry of FRP fabrication and infusions, we decided to go with a stick mold, basically, which is 2x4s and plywood and some PVC pipe to do the radii. And then over that was the tedious process of putting a hand layup of FRP so that we can have a mold that is vacuum or airtight. And over that, a gel coat and multiple iterations to surface finishes. So it was definitely a learning process. But some of the downsides with molds like this is that you can get a certain number of parts out of them, maybe one project, maybe two, and not a lot more. And so there was the first need for us having a better, more robust mold. And this is where we designed and ordered for fabrication a steel mold. Now this steel mold has been used for the other projects that I'll be talking about in a bit. Some of the advantages of having the steel mold is that we can weld inserts in the mold so that we can have different depths. The surface finish is superior to that of a gel coat, and steel molds can usually go up to about 100 or so infusions, sometimes more, depending on how well we'll maintain it. So that was the first step. Additionally, UMaine is actually still working and has some very successful trials with doing 3D printed molds. So that will definitely be a step in the future. The next thing I will talk about is materials and layup. The concern has always been, or the focus has always been, to use materials off the shelf, because the less or the more availability we have with materials, the more we can be price competitive. And so we have always used, since the start of the research, we have always used stitch fabrics. However, that comes with some limitations. We have worked extensively with some fabric weavers here in Maine, Tech Industries primarily, and we have transitioned for a number of our fabrics, instead of using stitch, to using woven fabrics and also 3D woven fabrics. Now, the 3D woven fabrics help with a faster wet out, and that allows for thicker laminates to be infused. It also reduces the labor because you can have thicker dry fabrics laid into the mold. And also you can get better fiber alignment as a composite technician is handling this material. The stitch fabric, sometimes the stitches are a bit loose and the fabric doesn't align as easily as you'd want it. So we've used woven fabrics for both carbon and some of our glass layers. Another thing that is common practice in the infusion industry is using infusion-friendly glue. I say friendly because anything going into the infusion will be a contaminant. However, it is such a low percentage that it doesn't affect the strength as much. However, you do need this glue to pre-infusion so that you can lay up all of your materials before you apply the vacuum bag and really compress all of those materials together. Now we still use that. However, we have minimized the use of these glues by also using polymer staples. Now these staples hold up better the layers of fabric to the foam core that we use in the webs, and that helps for a nicer or better compaction even before we put the vacuum bag on, and that leads to a better quality of infusion and also better looking radii. Another thing is the surface finish. When we did grist mill, Maine DOT wanted to go with a gray color at the time, but more importantly, we wanted to use a pigment to help with UV protection, and so that was the product. It was good. The standard was blemishes from a distance of 20 feet visually. However, since then we have been using an OPAM fabric, also comes from Textech Industries, and that OPAM fabric has allowed us. It's an opaque layer, so it does help with the UV protection, and it's the sacrificial layer on the outside. It's non-structural, but it also provides a very smooth, uniform finish with the least amount of time in post-processing. Another thing that we still work on with DOTs is that we have a quality control plan, and that is required by the DOTs. And for grist mill, for example, we did all 3 of these tests. We did panels separately on the day or with the infusion of the girders, using representative layups of the bottom flange, and we did D3039 for tensile strength. We did a representative layup of the web and did D778 and got the shear strength. And then we did a representative of the top flange and did D6641. As Bill talked about, shear strength is still more and more research. However, at least for now, using the D778, for example, shows that we are still keeping up to some standard value there of shear strength, even if all of these strengths have shown that we are using conservative numbers for design. Lightly touching on pultrusion, we see that pultrusion can be the future of GBeam production for a span range of 30 feet to 60 feet. It's more like standardizing a shape that can be optimal for that range. This is, as Bill said, a higher output, takes out a lot of the labor costs, and then we can have some standard shapes that would go for these ranges. Of course, there is a lot of research to go on there. We need to maybe optimize a cross section for this span range, but also for pultrusion. We have to accommodate thicker laminate sizes, because with pultrusion, there's a lot of concern with the friction as the material is pulled through the die. Introducing foam core in pultrusion can be tricky. It is doable. However, there should be some thought going into that. And what about camber requirements? How much can we have with camber coming out of the die? I'm going to talk now about the completed projects. I think we've talked enough about grist mill, but just real quick again, it was the first one. The project had a cast in place deck, and so the FRP girders, the GBeams were shipped to site and then placed on site. Contractor again was really pleased that they could, with the lightweight of the girders, just because he was the contractor was able to attach the utility connections and the utility pipe before setting the girders on the abutments. And so these 2 girders were set as a unit, and these outermost girders were also set as a unit. This is just a girder before it came out of our shop, and each girder was about 9,000 pounds. The next project we did was for a homeowners association. So it's a private bridge down in Sun Island in South Pasadena, Florida. It's the original project has 7 spans, and the 2 middle spans have had extensive deterioration because of all the salt water spray that gets up there from boats and jet skis. These spans have been built back in the 1990s. So really, that's not a lot of time for that amount of deterioration that happened, even with a number of maintenance efforts. So the challenge here was that we need to go in at this span and we have to match the depth of the different spans. And this is where we were able to use, composite design, which helps with optimizing for a section. Yes, this is a shallow section. It was only 12 inches, 12 or 13 inches deep for a 4 to 7 foot span. But by tightly spacing the girders, we were able to do that. Now, we manufactured these girders here in Brewer, Maine, and the two spans, it's a one-lane bridge. So each span had 4 girders, and both of those two span girders were shipped to Florida on one trailer bed. When they got down to Florida, the contractor found a site near to the construction site, and they set the girders up so that they can do prefabricated bridge units, PBUs. Each PBU was the full depth of the concrete deck with 2 of the GBeams, and these are the 2 PBUs as placed on site, and there's the closure pour in between. Did I miss something? Okay. And this is a quick, there wasn't a question about cost last time. This just touches on it for this project. There was a graduate student from Villanova University who actually did his master thesis. It was more focused on sustainability and life cycle for the GBeams and the current alternatives. He took this project in particular, and looking at the 3 bids that came from the 3 contractors, we gave them all the same price for GBeams. And you can see that the average bid for our solution came in lower than the stainless steel option. Of course, the carbon steel was the cheapest. However, the carbon steel would have had to be replaced maybe 3 times, whereas our girders have the 100+ year lifespan, same as what was assumed for the stainless steel. As for planned GBeam projects, the first one I'll talk about is here in Maine, and then the one in Rhode Island, and then 2 perspectives to follow. So the Twin Bridge project is also designed to be 6 girders, 3 PBUs delivered to site. So these are the 6 girders sitting outside of our manufacturing plant here in Brewer. And these were shipped down to American Concrete, and they placed a 4-inch precast deck on top of that. And this will constitute the PBU that will be taken to site in the upcoming, I think it's in around mid to late July. Once on site, they will cast an additional 8-inch concrete deck to be the structural deck, and and you can see also that some of these shear connectors, they are a bit taller, and those will be used for the screed, for screeding the concrete deck and using them to support the bidwell. The other project which is also going in around next month is a project down in Rhode Island. This is a 38-foot span. Also fabricated the girders here in Brewer and sent them down. The contractor ended up going with a precaster in New York. So right now the girders are in New York. This project also will be using PBUs, but as opposed to the Twin Bridge one, this will have a full depth concrete deck, which is the 8 inches, and with only closure joints on site. One project that we've designed and is now we're waiting for it to be advertised is down in Marco Island. This is an interesting project because it will be our longest to date. It's currently it's a 3-span bridge. However, they want to take the 2 center piers, giving us a clear span of about 103 feet. However, maintaining the same depth. So we've also had to maybe tighten the spacing a bit. but we were able to provide this solution for them. And we're also working on a design for the Rines Bridge in Augusta. This bridge will be interesting because the plan set will have both steel and the FRP option, the GBeams, and the contractor slash the owner will eventually decide what goes into this project. Bill, I think I'm done over here. I hope I'm giving enough time.
Yeah, thanks, Anthony. That's good. So that wraps up the presentation portion of today's meeting. We'd like to move on and address any questions, continue the panel discussion. We've got half an hour or so to do that. So we do have one question that's up in the chat, and I encourage all of you to type in your questions in the Q&A. First question comes in, it says there are shear deformations on the rib connection. If there are, how do the shear deformations affect the composite action? The short answer to that is the shear deformations are negligible. So there's virtually no slip between the concrete deck and the FRP girder. And we have measured that during fatigue and up through ultimate load in both shear block tests as well as in tests of full-scale beams, the 55-foot beam. And those deflections on the relative slip is on the order of hundredths of an inch. And so it's actually significantly less than what we see with the bearing type connection. It's a much more rigid connection. And we've also done a lot of other work. One of my grad students early on did some modeling as to what sort of relative deformation starts to significantly reduce the impact of composite action. And it takes a lot more relative deformation to reduce the effect of composite action than what we're actually observing. So it's basically perfectly composite. Okay, any other questions? Okay, I see another one popping in. Typical cost comparable to steel girders. And Anthony, you had a slide up on that, and maybe you can pull that up, because what was interesting is the variability in the individual bids. You focused on the average, but that was kind of interesting, right?
Yeah, I'll bring it back up here. Now this goes a bit different than what he was asking about, because the carbon steel and stainless steel here are actually referring to a concrete slab that is reinforced with carbon steel or reinforced with stainless steel.
Oh, okay.
Yeah, it was very interesting to see the different bids, especially, for example, for this contractor, he bid them both the same price. And maybe he assumed that working with something new, he didn't want to assume a lot of risk. However, the first contractor saw the advantages that we told them about and went with that. And let me reread the question.
Yeah, cost comparison with typical steel girders.
Yeah, so right now we still don't have the best metric to answer that, because but we are going to see after the Augusta Rines, or the Augusta Bridge in Augusta, because as I said, that contract or the plan set will have both the steel and the GBeams, and then we'll see how the bids come up. Another thing to take into account that maybe someone else in the chat knows, but the lead times for ordering and fabricating steel girders right now is a very long lead time. So that might also play into the decision making of different DOTs.
Okay, we have another question. Explain a little bit on the Florida Bridge, going from 3 to 1. How tall is your deck and girders? Maybe talk a little bit more detail about the span length, span to depth ratio.
Yeah. So for this project, the design, again, is 103-foot span. The girder itself will be 20 inches deep. And then there's a 10-inch concrete deck. The 10 inches are divided into a 4-inch precast and then a 6-inch cast in place. For a span that long, we really needed the 4-inch precast because we can't control deflections as well with the limitations set with this project. And they still needed it to have a finished profile with, as you can see, the vertical curve. They want to keep that camber in the final profile.
So is this one being designed around the usual AASHTO live load deflection limits, L over 800 on HL 93?
Yes, it is. It's actually with the curb and sidewalk, it is L over 1000, which is because it has a pedestrian sidewalk.
Okay. Yeah, so that's you probably got a pretty significant bottom flange in this one to help out as well, right? More
Yes,
carbon.
yeah, it is. What we took out in depth, we had to add in width. So the bottom flange alone is 2 feet wide in this project, which structurally is not the most efficient way. You don't design the girder with a lot more width, but given the project restraints, that's what we had to do.
Right, but it does illustrate how you have the flexibility to do that as well.
In design, yes.
So another question, I can partially answer this. Has there been interest from the rail sector and what new challenges might emerge for rail loads versus more typical highway loadings? Early on, there absolutely was interest from the rail sector, and they were particularly interested in the prefabricated units and being able to drop these in fairly quickly while they were lighter than maybe a more traditional material like steel or concrete. I don't know what the current emphasis. I know you're looking a lot more at highway applications, but I don't foresee there being any real major challenges with a rail application. And the GBeam, which is a different load carrying mechanism, it's not really a beam, but it is a composite shell that has been used in rail applications. So Anthony, maybe you could speak a little to that as well.
So we have had interest and we have been presenting at some of those conferences. The major thing is that the ARIMA requirements have to be met. And those are big physical tests that right now our research focus is not on it, but we can design for the loads. We have looked at that so far. So we can design for the loads. We can be optimal, especially with how we can use the girders and then the precast panels come in. So that can help with the construction timeline. But again, those need to be still tested and we haven't gotten to that point yet.
Yeah, and speaking for the ASCC where we do the testing, I'm confident we could test to those loads if there was a demand and it made sense and the funding was in place to do that. We might have to do something like rent an actuator because we might be pushing the bounds of what we already have, but we do have a frame that is capable of carrying more than twice the load we've ever put on one of these test specimens. So, so I'm confident that we could actually test to the loads required there. So another question, AIT, and I'll let you go with this one, Anthony. AIT is the sole fabricator of GBeams. As the market develops, is there an intent to develop and license other fabricators to increase cost competition?
Yes, that is true. We are the sole fabricators, but we are also very active players and we are trying to be even more active in ACMA. And so we believe that we do need to be working all together in composites and infrastructure. Yes, we will work on, there are some talks about doing more and more manufacturing plants, and there are some projects that we are looking at, prospective projects out on the West Coast, and it would be better to manufacture out there. If we manufacture out there, that means we hire a whole different crew. Maybe that crew is actually part of a company, and then that can be a licensing thing that happens then. And it's going to always depend on where the project is. And I think this is what I can say on my part. I think for the bigger vision of the company is more of the executive decision.
Yeah. Yeah, I understand. Of course, I mean, AIT absolutely has an interest in being cost competitive because that's how they're going to get more projects that way. So one thing that we saw with the concrete filled FRP arches is that as time went on, we did a lot of things to, understand soil structure interaction better and increase arch spacing from like 3 feet to 5 feet. And then we came up with better ways of fabricating those arches, and all of those things led to those becoming direct cost competitors with, in some cases more competitive than, steel buried arches and precast concrete. And so they're a viable alternative, and they do distribute manufacturing, or can distribute manufacturing around the country for those, and set up ways to do that. So I could see a similar thing happening with the GBeams. It all depends on how the market evolves.
I would also add that when AIT bridges started after the arches came out of the ASCC lab, AIT was actually not the fabricator of the arches, though the fabrication was being outsourced to different composite manufacturing companies. After a while, we saw that we can probably get a higher quality and more consistent product if we do it ourselves. And so AIT took on that big step to start manufacturing and not only designing. So yes, we are using infusion, we are using standard practices in the industry. Different people can be trained to do that. And yeah, we just have to see what the future holds on that.
Okay. Another question, is there any advantage to a hybrid FRP steel girder? I'm not sure. I think, one thing that FRP is used to do, it has been used to do, is strengthen steel girders. So a lot of the time when that is done, it's done because of a real weight advantage with the FRP, as opposed to getting relatively heavy steel plates up from underneath that have to be welded or bolted into place. You're working with lighter FRP. It's been used to enhance, stiffen webs, steel webs to prevent buckling, things like that. I think if there was an alternative for a hybrid FRP steel girder, it would have to be a pretty unique case where you're not so worried about the durability benefits you get from FRP, because you still have steel there, which is subject to corrosion or other durability concerns, but it needs to play some unique role. And one challenge with FRP and steel also is, how do you attach them together? How do you bond them so that they behave together in the long term? Because there you really rely on an adhesive bond. And that's something that I'll come back to, that corrugated top flange concrete shear connector. That's an example of how we really avoid using any bond there, right? We're relying on a mechanical connection. And in fact, if you look at, there are a couple examples, just a couple of FRP tub girders that have been put out as pilot projects around the world. I think, one in Spain, one in Poland, one in the US. The closest one to what we've done is in Poland, but they actually had to bond steel to the FRP with adhesive, and then they had steel shear studs sticking out of their steel plate on the top. And we looked at that and we're like, oh, no, we're going to avoid that. Last thing we want is an adhesive bond line that we don't understand the durability and longevity of. So that's always a challenge with steel and FRP. I don't know, Anthony, if there's anything you could add to that.
Yeah, no, honestly, we have joked around about adding steel to our bottom flange, because at the end of the day, steel is at 29 MSI. It's just
right.
stiffer.
Yeah, low modulus is the thing with FRP a lot.
Yeah, exactly. And I just want to highlight what you already said, Bill, is that will end up being a fatigue nightmare, that bond between a steel layer that's in with the resin there. So
yeah, and actually this brings me back to another question that was asked last time, which is difference in coefficient of thermal expansion between concrete and FRP. And actually I took some time and did some back of the envelope calculations on that since the last webinar. I want to come back and touch on that, because this is an important aspect when you try to join dissimilar materials, right? So the unidirectional carbon probably actually, if anything, has a small negative CTE or virtually zero CTE. In other words, if you heat it up, it might actually shrink a little bit, right? Or cool it down, it might expand a little, but it really is basically a zero coefficient of thermal expansion. The glass, on the other hand, is different and very hard to quantify, because you got plus minus 45-degree webs, and you have a layup in the top flange. It's a combination of things. And then you've got the concrete, which undergoes shrinkage and cooling and heating. So I did a quick calculation where I said, okay, here's an FRP girder bridge with the dimensions of the Hamden grist mill. It's built at, a typical AASHTO provisions for the state of Maine. That would be expected to cool by 60 degrees uniformly from its construction temperature. So I imposed a pre-strain of corresponding to 60-degree temperature drop in that concrete, and ignored any thermal movement in the girder. So in other words, that concrete's going to shrink, and then that's going to cause basically bending like this, and it's going to put tension in that bottom flange carbon because it's not going to move. The concrete wants to move and it's not. And you can go through the calculation in force plane sections with this non-uniform shrinkage strain due to temperature. And it produced a stress in the carbon bottom flange at the end of the day, which was a fraction of a % of its UTS. So it's very small. So it turns out that those differential movements don't have a big effect on the FRP. They really don't. On the other hand, it may not take much when you bond it to steel if there's some dissimilar movement. When you're talking about a bond line, it could be a very different situation. If you set up some cycling shear strains there, and then when you have loading induced fatigue, that can be problematic.
Yep.
So yeah, I understand the steel might be necessary for other reasons, but maybe the steel is on top of the girder and the steel is not structural. I don't know, but making them behave together would be very challenging.
Yep.
And behaving together and being structurally efficient together, that would be tough. Okay, I think that's all the questions. Anything else? Okay. I'm not seeing anything pop up. If you have more, please feel free to email them to us. We will. Okay, have you tried CFRP? Well, we are using carbon in the bottom flange of the girder. So that is carbon fiber reinforced polymer. Anthony, I don't know if you want to. Okay. So yeah, this is a hybrid girder. It's got carbon where we need it. It's got glass where we need it. I think we're there on the questions. If you have any more, please feel free to email them to us. And again, if you want any of the public domain documentation out there, I'd be happy to send you copies of everything that's available. Just shoot me an email. I'm easy to find. And the screen share has popped up now. I want to just take a minute to remind everybody that we do have a conference coming up August 9th through 11th. The main conference days are the 10th and 11th when all the presentations will be. That will be at our 4th annual TIDC conference here in Orono in August. And the website's up, the registration information is there. And I believe you're all going to receive a follow-up email with a link to that so that you have all that information at your fingertips. And if you choose to come, it'll be easy enough to do so. So with that, I think we will close out the webinar. I appreciate everybody's attention. And thank you, Anthony, for coming on board and doing a great job with your aspect of the talk.
Thank you.
All right, bye-bye.
Thank you, everyone.